solving equations using logs, that's what we are going to be doing today. Now, why are logs so important? So you've seen equations like this before in your O-levels. So if you had something like this, for instance, 3 raised to power x equals 81. How could we solve this equation? We could say this: the right side can be written as 3 raised to power 4. That's a perfect power of 3. 3 raised to power 4 gives us 81. And then we could say, since the bases are equal, the powers should also be equal, and x equals 4 from here, right? So if we could write 81 as 3 power 4, then since the bases are same, we could say the powers are same as well. So x equals 4 in this case. Similarly, if you had something like this, 4 raised to power x equals 1 over 16, let's say, what could we do for this? We could say this is 4 raised to power x equals 1 over 4 squared, and then we could write it as 4 raised to power x equals 4 raised to power minus 2. We've got the same base on both sides, so the power should also be equal, and we could say x equals minus 2, right? So we know how to solve equations like these. But now, what if you had something like this? You had 3 raised to power x equals 10. What do you do with this now? 10 cannot be written as a power of 3. So we can't solve it using the method that we have discussed before. In such cases, what we do is we take log on both sides. Now, why does that work? Because remember the power law. What does that power law do? If x is in the power, that comes down when we have log applied with it. So right now, the problem is x is in the power. We can't handle this directly. So what we do is we take log on both sides of this equation. Let's do that and see what that gives us. It becomes ln of 3 raised to power x equals ln of 10. So generally, I'll be taking ln. So this is the log with base e. You could take another log as well. So generally, you can use lg as well, and that's also fine. If you're familiar with that, but this is going to be enough for us. If we just use ln every time, that is going to be enough. Ln, what does that represent? Remember, ln means log with base e. It's just a short way of writing log with base e. So I'll be using ln whenever I take log, unless the question has another log already taken. Okay, in that case, we could use that log, whatever they have there. But otherwise, we will be using ln wherever we have to use logs. Okay. Now, what do we do here? We just take log on both sides. Now, how does that help? We could use the power law here. We have 3 raised to power x. This power could come here and get multiplied with ln of 3. So that it becomes x times ln of 3 equals ln of 10. Now you could just take this ln 3 on the other side. To the other side, it becomes x equals ln of 10 divided by ln of 3. You could just evaluate this from your calculator and you get the value of x that satisfies this particular equation. You just take ln 3 to the other side divided by ln 3 to the other side, it becomes ln 10 over ln 3. You evaluate these two things. The value of ln 10 here turns out to be, let me check again. It's 2.302 divided by ln 3. Just evaluate this on your calculator, 1.099, and this is going to give me 2.10. So this is the value of x that satisfies the equation that we were trying to solve there. All right, so if you were to input x equals 2.10 there, that would satisfy this equation. All right, so this is the simplest kind of equation that you could solve using logs. It's not 10 is not a perfect power of 3, so we could not solve it directly, but using logs now, we can solve such equations. All right, so this is one possible equation you could solve using logs. Now let's take another example. Let's say we've got something like this. We have ln of x equals 3, for instance. Now, there are going to be some equations that already have log in them. All right, so this is one such equation that already has log in it. Now, how do we deal with this? Remember that conversion that we did from the log form to the index form? What did we say here? So if you have to convert log form to the index form, how does this work? The base of log goes to the other side and becomes the base of the number that you've got on the right side. So this b becomes the base of that number there on the other side, right? That's what happens. Now, think about this. You've got ln of x equal to 3. What is ln? ln is the same thing as log with base e, right? That's what ln is. So it's log of x with base e, that equals 3. Now, if you were to convert this to the index form, all we have to do is take this e to the other side. It becomes the base of that number 3 on the other side. And we have x equal to e raised to power 3. So the log form can be converted to the index form like this. Okay, so the log gets eliminated because we've converted it to the other form now, to the index form. And now you've got x equals e cube. We just evaluate this on your calculator. And this turns out to be 20.08. That's the value of x that you get from this equation. All right, let's take a similar example to this. Let's say you've got something like this. It could be some other base as well. Let's say you've got log of x with base 3, that equals, I don't know, let's say 2. What about this? How do you solve this equation? You take this 3 to the other side. It becomes the base of 2. And the value of x turns out to be 3 squared, which is 9. All right. So if you have log on one side and a constant on the other side, this is what you do. You take the base to the other side and make it the base of the number in index form on the right side. All right. Okay. Now let's take another example. Let's say you've got something like this now. ln of 2x plus 1, that equals ln of x plus, or let's say x minus 3. Let's say this is an equation that we have. Is this going to have a solution? No, x plus 3. This is going to work. Yeah, ln of 2x plus 1, that equals x plus 3. This is an equation that we have. Now, the equation already has log in it, right? So it's ln of 2x plus 1 on the left side, ln of x plus 3 on the right side. How do we solve this equation? Now, one way to think about this is that one way you might think about it would be that you say the log gets cancelled, okay? Now, although you could do it like this, but it's not quite mathematically correct because log is not a number that you can cancel like this. The argument that you actually have for this is that on the left side, you have ln of 2x plus 1. And on the right side, you've got ln of x plus 3. If the log of both of these things are equal, that means the expressions inside, they should also be equal. So that gives you 2x plus 1 equals x plus 3. And this is going to give you a value for x, which is 3 minus 1, which turns out to be 2. X equals 2 would be a solution to this equation. So when you have a single log term on both sides, all you have to do is just equate what you've got inside. All right, equate what you have inside. and that is going to give you the result. I would recommend that you don't think of it like canceling this thing, because that might cause some problems. For example, let's take another case. Let's say you've got an equation like this. Let's say you've got ln of 2x plus 1 that equals ln of x plus 3, and let's say plus ln of 5x minus 2. So I've added another term here on the right side. Now, how do we solve this equation? Now, if you were thinking of canceling ln in the previous step, that would be the same as canceling this log, because now you've got log in every term. So you might have this urge of just canceling out the logs and then writing it as 2x plus 1 equals x plus 3 plus 5x minus 2, but that would be wrong. You cannot do that. Again, as I said, ln is not a number that you can cancel like this. So it doesn't work like this. You cannot do this. So what do you do instead? What you'll have to do is you'll have to convert both sides to a single log. All right. In the previous example, we had a single log on both sides. We had ln of 2x plus 1 on the left side and ln of x plus 3 on the right side. If we can convert it to a form like that, such that we have one single log on both sides, we can just equate whatever is inside those logarithms. Okay. Now, in this example, we have one log on the left side, but we have two log terms on the right side. So let me just write that down here. So you keep this in mind. You need a single log term on both sides. Right now, you've got 2 on the right side. Now, how can you make it a single log term on the right side? Think of a law that you know about. You've got addition outside the log. The two logs are being added outside. That should remind you of the multiplication law, right? So if you have addition outside the log, if I were to make it a single log, inside this log, we would have multiplication. So I could write it as a single log like this. I could say this is ln of x plus 3 multiplied by 5x minus 2. And now we've got a single log on both sides. All right. And now we could say, since log of this and log of this, they are the same, then these expressions that we have inside, they should also be the same. So 2x plus 1 should be equal to x plus 3 into 5x minus 2. And now that's a simple quadratic equation that you can solve and find the values of x from. Okay, so you first need to convert it to a single log term on both sides. Once you're done with that, then you could get rid of the log like this, because if the log of this expression and this expression, they are equal, then the expressions inside also should be equal. All right. Please don't cancel logs like this in the first step. That would be incorrect. Log is not a number. You cannot cancel it like this. You have to first convert it to a single log term, like we've done here. And then we could say, since log of this term and log of this term is equal, the expressions inside should also be equal. So that's the proper way of doing this. Okay. And now we could just simplify the right hand side and see what that gives us. 2x plus 1 equals x into 5x, that's 5x squared, plus 15x minus 2x, that's going to be 13x, and then minus 6. Take everything to one side so that it becomes a quadratic equation. We have 5x squared plus 13x minus this 2x. That's going to make it 11x minus 6 minus 1, that's minus 7. So we have 5x squared plus 11x minus 7 equal to 0. This is the equation that we're getting. Now let's write everything on one side. We have 5x squared plus 11x minus 7 equal to 0. Okay, it's a quadratic equation. You can think about whether you can factorize this. 7 and 5, that's 35. You can't really factorize this. Okay, so factorization is not possible here. So what is the alternative? We could use the quadratic formula that gives you minus 11 plus minus square root of 11 squared minus 4 into 5 into minus 7 divided by 2 into 5. And when you solve this, you get two answers at the end, which are x equals 0.516 and x equals minus 2.72. All right. Now, when you are solving equations that have log in them, especially if the log is already there in the question that's there, you have to be very careful with your final answers at the end, because it is sometimes possible that one of the values of x that you're getting at the end, it gives you a negative value inside the log. So for instance, in this case, you're getting two answers, 0.516 and minus 2.72. What you have to do is you have to input both of them in each of these log terms to see in case any of them become negative when you input that value. So if you input 0.516, now the first log remains positive, the value inside that remains positive. The second also remains positive. You have to be a bit careful about this because it has a negative sign. So 5 into 0.516, that's going to be somewhere around 2.5. Then minus 2, that also is something positive. So 0.516 is not causing any problems. This is going to be one of the solutions. Now you have to check minus 2.72 as well. Now, if you were to input minus 2.72 in these terms, if you input it here, 2x plus 1, if x equals minus 2.72, this term is going to become negative. All right, if you were to input minus 2.72, the first term here, the expression inside the log, that's going to become negative. So you cannot have minus 2.72 as a possible answer here. What you have to do is you have to ignore this answer. You have to say that this one is not possible. You will not write this as an answer. Now, this is something that you have to do every time when you're solving an equation that has log in it. You have to verify your answers at the end. So in this case, minus 2.72 is not going to work because this makes ln 2x plus 1 negative, or in fact, not this negative, it makes the part inside, which is 2x plus 1, it makes that negative, and then this would become undefined. It also makes 5x minus 2 negative, and that also becomes undefined. So this answer is not possible. Whenever you have log equation and you get any answers for that, you always have to verify those answers. Now, it's not necessary that you will always have to ignore negative values of x. That's not something that would always work. For example, if you had an equation like this, that's as an example, if you had ln of x plus 2 equals ln of 2x plus 11, and you had minus ln of x plus 5. Just as an example, let's assume you ended up getting an answer which was minus 1.5 for this, right? It's just as an assumption. Now, you would not just ignore this answer because it's a negative value. Why? Because even if x is negative, it's not making any of these expressions negative. If you were to input minus 1.5 here, this thing remains positive. If you input minus 1.5 here, this remains positive as well. And if you input minus 1.5 here, this also remains positive. So this is still going to satisfy this whole equation. So you have to check by inputting value there does it make any of these logs negative? If it does make any of them negative, the expression inside negative, then you would say you have to ignore that, okay? But you don't necessarily ignore a value just because it has a negative sign with it. You have to check by inputting in the original equation to see if it would work or not. All right, so in this case, minus 2.72 does not work. You would say the only answer that you have in this case is 0.516. So that's your final answer here. All right. I hope that makes sense. Now let's try another one. Now let's say we've got this equation. So now I'm going to write another equation here, and it looks like this. Let's say you want to solve ln of x equal to 6 plus ln of 2x minus 1. We want to solve this equation now. Now you see, in the previous equation, we had all the terms had log in them, right? Now in this one, there are some terms that have log in them, and then there's one term that is just a constant. How do you deal with a problem like this? Now, there are multiple ways of going about this. One possibility is that you take all log terms to one side, right? That's one possibility. That's one way to deal with it. You can write that down here. You take all log terms to one side, right? And once you're done with that, you make them a single log, all right? So take everything to the left side. In this case, for instance, it becomes ln x minus ln of 2x minus 1. On the right side, then you have just 6. Now, can you make it a single log here? You've got minus outside the log. You could write it as ln of x over 2x minus 1. You could write it like this, right? Using the division law, subtraction outside log, it becomes division inside the log. This equals 6. And now this is exactly the form that we have seen before here. You have log on one side and a constant on the other side. E is the base. We have ln there, E is the base. You could take that base to the other side and make it the base of 3, the number that you've got on the right side. Right, so ln has a base E, remember? You can take this base to the other side. Sorry about that. You can take this base to the other side and make it the base of the number 6. And that is going to get rid of the log here, and you're going to be left with x over 2x minus 1 equals e raised to power 6. Okay, so now the log term is gone. Now you can just solve this equation. It's actually a linear equation. If you take 2x minus 1 to the right side, it becomes 2e raised to power x times x, 2e raised to power 6 times x minus e raised to power 6. Let's just add one more step here to add more clarity. It's x equals e raised to power 6 into 2x minus 1. And you just multiply them. It's 2e raised to power x times 2e raised to power 6 times x minus e raised to power 6. Now you need to solve this. You can take the x terms to one side. That's x minus 2e raised to power 6 times x. On the other side, you've got minus e raised to power 6. Take x common here. You want to find the value of x. You can take x common. And that leaves you with 1 minus 2e raised to power 6. And on the other side, you've got minus e raised to power 6 divided on the other side. You get minus e raised to power 6 divided by 1 minus 2e raised to power 6. Just evaluate this on your calculator. And that is going to give you the value for x that satisfies this equation. Okay, now let me try this. This gives me minus e raised to power 6 over 1 minus 2e raised to power 6. This turns out to be 0.501. And that is your final answer here. X equals 0.501. All right. This is one way of dealing with a problem like this. You have log in some terms and you don't have log in another term. You take all the log terms to one side. That's how you start. Once you're done with that, you make it a single log. The log that you have on one side, you make it one single log. All right. And then you take the base to the other side, make it the base of the number, base of the number that you have on the other side, then just solve it like a normal equation after that. All right. That's one way to deal with it. There's another way of dealing with problems like these as well. And that looks like this. Let's write that equation down again. You have ln of x, or write it here first. Ln of x that equals 6 plus ln of 2x minus 1. This is what your equation is. All right. So one way was to take all the log terms to one side and then make it a single log, and then use that conversion from log form to the index form, and you get the result from that. Another idea is that you use a trick that looks like this. Remember, ln e, what is that equal to? Ln e is equal to 1, right? Because the base of ln is e. If you take ln of e, since the base and this number are the same, the result is going to be 1. You can try this on your calculator as well. The value of ln e is 1. So another idea that you could use here could be that you write 6 as, you convert 6 to a log form as well, right? So 6 is right now without a log. You convert 6 to a log form as well. How does that work? You could write 6 as 6 multiplied by ln of e. Can we do that? It's just like saying 6 multiplied by 1, right? That's still 6. Ln e is 1, right? So if you say 6 times 1, that is still 6. Instead of 1, we are writing ln of e. And we have plus ln of 2x minus 1. Okay. And now what you can do is you can take this 6 to the power here. So it becomes ln of e raised to the power 6 plus ln of 2x minus 1. And now you can use the product rule to have one single log, the multiplication law, to have one single log on the right side. You could write it like this. You could say this is ln of x equal to ln of e raised to the power 6 into 2x minus 1. And you have one single log on both sides now. And you could get rid of the log term. Okay, so that it becomes just x equal to e raised to the power 6 into 2x minus 1. So you've actually converted it to the form that was here. One single log on both sides, you just equate the part that is inside the log. All right. And this is what you end up getting from that. So the trick is you multiply the constant with ln e, and that helps you convert 6 to ln e raised to power 6 using the power law. Okay. And then you use the multiplication law. After that, you've got addition outside log, it becomes multiplication inside, and you get something like this. Now, this is exactly the same as before. You could just simplify this. X equals 2x e raised to power 6 minus e raised to power 6. That's exactly what we had here as well. You can just solve it further, and that will also give you 0.501, what we got on the left side here. So this could be another possibility as well. You could also do this. By the way, there's a point here that you need to keep in mind, and that is we could not use the multiplication law at this step without taking 6 to the power. Okay, that's an important thing to remember. In order to be able to use multiplication law or the division law, you can't have any number multiplied with these logs. Okay, otherwise you cannot do that. For example, if you have different numbers here, if you have 2 here and 5 here, then you can't use the multiplication law yet, unless you first take 2 to the power here and then 5 to the power here, and then apply the multiplication law. So in order to use multiplication law, you need 1 with both of them. Okay, so if there's any other number, you first take it to the power and then use that law. And it's the same for the division law as well. You need to have nothing outside. So nothing, or you can say 1 outside. If it's anything other than 1, you have to take it to the power first before you can use the multiplication law or the division law. Okay, so that's important. So that's why in this case, before applying the multiplication law, what we're doing is, sorry about that. Yeah, so in this case, before applying the multiplication law, you are first taking 6 to the power here, and then you're using that multiplication law. All right. Now, this was an overview of a number of different types of equations that you would need to solve using logs, but that's not it. There are more. Let's take another example. And for that, I'm actually going to use something from the worksheet. Let me just check if I can find one question from there. Okay, so let me actually just write it down there. I can just add another one here. Okay, now let's try this. Now let's say we want to solve an equation that looks like this. 3 raised to power x equals 2 plus 3 raised to power minus x. This is an equation that we want to solve now. Now again, you've got x in the power. So you have to use log here somehow. But the problem with this is, if you were to apply log on this directly, what would happen? Remember, log cannot be applied to individual terms. It's a function that you have to apply on the whole thing on both sides. So just like squaring 2 sides of an equation, if you were to square both sides, you would say 3x whole power 2 and 2 plus 3 power minus x whole power 2. You could not do it like this, that you're squaring this term and then squaring this term and then squaring this term. It doesn't work like that. That would be wrong. You can't square individual terms or apply any function to individual terms. That's not possible. Whenever you apply a function, you apply it on the whole thing. So if you were to apply log here on both sides, on the left side, you would have ln of 3 raised to power x. On the right side, you would have ln of 2 plus 3 raised to power minus x. You could not have ln of 2 plus ln of 3 raised to power minus x. You can't do it like this. Okay, ln is going to be applied on this whole thing. But if you were to do this like this, if you were to take log directly here, now you're stuck. You can't do anything. You've got a plus sign inside the log. There's nothing you can do after this, right? There's nothing you can do after this. There's no way you can simplify this. Remember, multiplication law, when did we used to do that? Use that when we had addition outside log. In that case, we could use the multiplication law. This is addition inside log. There's no way to simplify this. Let me just remind you about that. I showed you an example like this here as well. If you have ln of x plus 5, for instance, you can't do anything with it. You can't simplify this. All right. And that is what is happening here as well. You can't simplify this if you were to take log on both sides. So this is not going to work. Now, what do we do instead? In such situations where you cannot use log on both sides, and that is going to be generally when you have a plus sign or minus sign in the middle, if you were to take log, you'll have plus or minus inside log, and then that is not going to work. So what do we do here instead? If we can't use log, what else could we do? What we do in such cases is we use a substitution. In this case, we could say, let another letter, another variable, let's say u, equals 3 raised to power x. Okay, let u equal 3 raised to power x. Now, how does that help? On the left side, you got 3 power x. That could be written as u. On the right side, you got 2 plus 3 raised to power minus x. Now, you can actually change it to that form first. I could write it first as 3 raised to power x equals 2 plus 1 over 3 raised to power x, right? So it's 3 raised to power minus x. I could write it as 1 over 3 power x. And then I could say, let's assume another letter u equal to 3 power x. And when we do that, it gives us u equals 2 plus 1 over u. And now it's a simple equation that we know how to solve. You could multiply u with all the terms, and that gives you u square equals 2u plus 1 to get rid of the fraction. So I've just multiplied all the terms with u. That gives me u square plus 2, u square equals 2u plus 1. Now take everything to one side. It becomes u square minus 2u minus 1 equals 0. Now this is a quadratic equation that we can solve. Let me see if we can factorize this. We could not. We can't factorize this. So we have to use the quadratic formula. Let's input values minus into minus 2 plus minus square root of minus 2 whole squared minus 4 into 1 into minus 1 whole divided by 2 times 1. Now this gives us two values for u. Let's find out what they are. It's 2.414 and minus 0.4142. These are the two values of u that we get from this. Now remember, we were not solving for u, we were actually solving for x. So at this point, we need to put that substitution back. We assumed u to be 3 power x, so we could say 3 raised to power x equals 2.414 or 3 power x equals minus 0.4142. And now we could take log on both sides to find the value of x. So if we take log on this equation, ln of 3 raised to power x, that equals ln of 2.414. Now this x is going to come down here. So that it becomes x times ln of 3 equals ln of 2.414, and then x equals ln of 2.414 divided by ln of 3. You can evaluate this and you'll get a value of x from this. Now let's see what this turns out to be. ln of 2.414 divided by ln 3, this is 0.802. That's one value of x that we get. Now let's look at the other equation that we have. 3 power x equals minus 0.4142. Now, if you were to take log on both sides in this case, ln of 3 power x equals ln of minus 0.4142. Now, this does not give you anything. You can't take log of negative numbers, right? So this is not going to give you anything. This is not possible. So you don't get any values of x from this second equation. This is not possible. All right. Now you could actually you could either show it like this if you wanted, or you should actually just know if you have any positive number, no matter what power of that number you take, you can never end up getting a negative result. That's not possible. Okay, so you would not get anything from this. If you don't remember that, just try taking log. You'll realize that this turns out to be a math error on your calculator. It's not going to work. So the solution for this would be x equals 0.802. That's the answer that you get from this. All right. So this is another thing that you sometimes have to do, that you have to use a substitution, like we did in this case. When does that normally happen? When you have something being added or subtracted here, because that causes a problem that you end up getting a plus sign or a minus sign inside the log. And that's something that you cannot solve in, right? So you can't do anything with this afterwards. Okay, that's why it doesn't work. So in such cases, if there's only one base that has some power, you can use that as, you can replace that with another variable, like we did in this case, u equals c power x. You can use that substitution to solve that equation like this. All right, so that's another way of solving equations that involve powers like this. So in this case, you have to use substitution like we did in this case. Okay, one last example and then we end. Let's try. Okay, let's try this. Let's say you have 2 raised to power 5x equal to 3 raised to power 2x plus 1. You want to solve this equation now. Now, how do we solve this equation? Now, is substitution going to be helpful here? Not quite, because in this case, you've got 2 different bases. You've got 2 here and you've got 3 here. Now, what do you choose as a substitution? So in the previous case, you had the same base. You had 3 power x and had 3 power minus x. You also converted that to 3 power x. Then you could use a substitution after that. In this case, you've got 2 different bases. So if you were to use a substitution, you would have to use 2 different substitutions. And that would introduce 2 variables that you cannot solve further than. If you have 2 variables and 2 unknowns in one equation, there's no way to solve that. So what do we do in cases like this? In this case, you could actually just take log directly. Why? Because in this case, if you were to take log directly, that would give you ln of 2 raised to power 5x. On the right side, you have ln of 3 raised to power 2x plus 1. And we don't have that problem that we had in the previous case. In this previous example, we ended up having a plus sign inside log. And that was something that we could not do anything about. But that's not a problem here. In this case, it works, right? So there's only one term on both sides. So you could just take log directly. Now, when you take log directly in this case, what happens? This power is going to come down on the left side. Sorry about that. This power comes down on the left side, 5x. And that is going to give you 5x times ln of 2 on the left side. On the right side, 2x plus 1. This is the power. This comes down here and gets multiplied with ln of 3. Now, be sure to use brackets here, because 2x plus 1, this whole thing is being multiplied with ln of 3. All right. And now you can solve this equation. You can either convert it to decimals first, or just keep it like this and make x the subject and just evaluate everything directly after that. 5x into ln of 2. On the right side, you have 2x into ln of 3 plus ln of 3. Take all log terms to one side. All x terms to one side, because we're looking for the value of x. Take all x terms to one side. That gives us 5x ln of 2 minus 2x ln of 3. And on the other side, we have ln of 3. Now we can take x common from the left side, because we are looking for the value of x. So we can make x the subject. And that gives us x into 5 ln 2 minus 2 ln 3 that equals ln of 3. And the value of x then turns out to be ln of 3 divided by this whole thing, which is 5 ln 2 minus 2 ln of 3. You can put this whole thing on your calculator and see what that gives you. ln 3 divided by 5 ln 2 minus 2 ln 3. This gives me 0.866. That is the value of x that we're getting from this, and that's going to be the solution to this equation. All right. So this is how we solve different types of equations that involve this log function, or it has x in the power. All right. Now, let me just quickly go through all of them just to give an overview of what we've done. So we started from this one simple example where we had 3 power x equals 10. We saw how to solve this one. We could just take log on both sides, and that gives us the result. Then we saw this one. When we have log on one side and a constant on the other side, you take the base of the log to the other side and make it the base of the number that you have on the other side, and then it converts to the index form. That was another case that we did. Then if you have a single log term on both sides, you could just get rid of that log term and say the expressions inside are equal, then solve that further. If you have multiple log terms on both sides, what you do is you convert them to a single log term first of all. Okay, on both sides you should have a single log term, and once you're done with that, you just equate the part that is inside log. Okay, you equate the parts that are inside log, and then you solve them further. Now, again, this is something that you have to be careful about for all such problems which have log in them. In the question itself, you have to verify your answers. Sometimes with some of the answers that you get, a log ends up being undefined. Okay, so you have to ignore those answers. That's going to be necessary. In this case, minus 2.72, it makes some of these logs undefined, so you have to ignore that answer. Then we did another case in which we had log in some terms, but not in all of them. One way to deal with this was to take all log terms to one side and then make them a single log like this, and then use that conversion from log form to index form, that the base of the log goes to the other side, becomes the base of this number, and then you solve it like a normal equation after that. All right. You could convert it to decimals as well. You could find the value of e power 6 in decimals first if you want. If you're more comfortable that way, that's also fine. You could do that. Or you could just do it like we did here, keeping in terms of e, and then at the final step, you could evaluate everything on your calculator. You could solve it like this. It's your choice if you want to keep it in terms of e until the end, or convert it to decimals already and then simplify it afterwards. That's something that you can choose. Another method for solving this equation was that you convert this 6 to log form as well. How does that work? You multiply by ln e, which is actually 1, and then take the 6 to the power, and then use the multiplication law. And after that, just get rid of the logs. After making them one single log on both sides, you just equate the parts that are inside the log. Okay, so this is what we did. Then we talked about substitution that you have to use sometimes. When you have an expression like this, some equation in index form in which you have plus or minus in the middle. In that case, you have to use substitution. So you have indices, and then you have plus minus in the middle. You need to use indices here because applying logs directly here is not going to be helpful. In that case, you would end up getting this expression inside the log, and you can't simplify that anyway. In such cases, you have to use substitution. Okay, that is going to be necessary. Now, once you understand those problems that we discussed, you should be able to do most of these already, but we'll just try a couple which are slightly more complicated. So let's do this, for instance. Question number 19. Let's try this. This is question number 19 from the worksheet. Okay, so it says solve the equation 5 raised to power x minus 1 equals 5 raised to power x minus 5. Now, how do we deal with this? Now, you see, if you were to take log on both sides, you would have a problem, and that would be that you would have a minus sign inside the log. You would have a minus sign inside the log like this, and then you can't do anything with it. You can't simplify this, and it won't work. All right. So you can't take log directly on this. That is not going to help. All right. So what else can we do in this case? What we can do is we can use a substitution. Why? Because we've got only one base, 5 power something, and we've got 5 power something. You can change this equation a bit, or you can change this particular term a bit. You can say, let's write this as 5 raised to power x multiplied by 5 raised to power minus 1. Using the indices rule, right? So if you have x raised to power a into x raised to power b, that can be written as x raised to power a plus b. In this case, it was written like this. We are converting it back to a form like this. We're basically splitting it. We're saying it's the same thing as saying 5 power x multiplied by 5 power minus 1. On the other side, you have 5 power x minus 5. Now, the left side can be written as 5 raised to power x over 5. On the right side, you have 5 power x minus 5. And now what we can do is we can use a substitution. We can say, let another variable, it could be any variable, let's say y or anything else, let y equals 5 raised to power x, or u equals 5 raised to power x, anything that's not already used in the question. Okay, so we often use u for a substitution. Let's use u here for that. Okay, so what happens now? This converts to u over 5. On the other side, you've got u minus 5. Now it's a simple linear equation that you can solve. Multiply 5 on the other side, that gives you 5u minus 25. And that gives you 4u equals 25. And u turns out to be 25 over 4, which is 6.25. So you've found the value of u from this. And now using this value of u, you can find the value of x, because what was u essentially? U was just 5 raised to power x. So 5 raised to power x equals 6.25. This is a simple equation that you can solve now using logarithms. Take log on both sides. That gives you ln 5 raised to power x equals ln of 6.25. X comes down here, gets multiplied with ln 5. That leaves you with x ln 5. On the other side, you've got ln of 6.25. And then x equals ln 6.25 divided by ln of 5. And that's going to give you the value of x that you were looking for. Okay, you can just evaluate this and see what that gives you. Let me just try. ln 6.25 over ln of 5. This is giving me 1.14. All right, so that's your answer here. So you had to use a substitution. Why? Because if you were to take log here directly, you would have a minus sign inside log, and that's something that you cannot simplify. So you instead use a substitution because it's the same base with all powers. Wherever we have x in the power, it's the same base 5. So a substitution works in this case. All right, let's take another example. So this was question number 19 that we just did. Okay, now let's have a look at another one. This we've already done. Let's try this. Question number 33 from the worksheet. 33. Okay, now this says solve correct to 3 significant figures this equation. Now, what's the equation? It's e power x plus e power 2x equals e power 3x. Now, again, we've got the same problem. If we were to take log on both sides, we have a plus sign here, and that's going to cause problems. We would not be able to simplify anything. So what can we do instead in this case? We could actually start by writing these terms slightly differently. We could say it's e power x plus e power 2x could be written as e power x whole squared, right? So since you have plus in the middle, you can't use logs. What you can think about is that you have to use substitution here as well. Okay. Now, what substitution could you use? You could substitute e power x with another variable. Now you've got e power x here. That's fine. You could replace it with another variable. But what about e power 2x? And what about e power 3x? For that, what you do is you write e power 2x as e power x whole square. And similarly, you write e power 3x as e raised to power x whole cube. All right. You just write it a bit slightly differently. And now you could say, let's use a substitution and say, let u equals e power x. What does that give us now? That gives us u plus u square, and that equals u cube. This is a cubic equation now. You can see how to solve this. Take everything to one side. That gives you u cube minus u square minus u equals 0. And now you could take u common. That leaves you with u square minus u minus 1 equals 0. Now we've got two factors that are being multiplied and the result is equal to 0. That means either this first thing is equal to 0 or this thing is equal to 0. One of these has to be true. So we say either u equals 0 or u square minus u minus 1 equals 0. Now this we already have now. Let's solve this equation and see what we get from this. Can we factorize this? We can't. So we have to use quadratic formula. We put values in the quadratic formula. U equals minus into minus 1. That's minus b plus minus square root of b square minus 4 into a into c. All right, this is what you have in the numerator here, divided by 2 times a, which is 2 times 1. Now you just solve it using a calculator and get the two values of u from your calculator. You can write them directly here after this step. Let's see what they are. U square minus u minus 1 equals 0.
So 1.6 and minus 0.6.
1.6 and
Minus 0.6.
minus 0.6. Vadeep, you are going to lose 1 mark for this because your answers are not going to be accurate. This is not your final answer yet. You want at least 4 significant figures in your working. This is definitely going to give you a wrong answer at the end, an incorrect, not an inaccurate answer at the end. Not wrong, but inaccurate, and that's going to make you lose 1 mark. So you have to have at least 4 significant figures. So the first one is actually 1.618. All right, so we have to write the whole thing. And then the second one is minus 0.6180. All right, these are the two values of u that we have. Now, we've got 3 values of u. We were looking for the values of x here, right? we put that substitution back. We say either e raised to power x equals 0 or e raised to power x equals 1.618 or e raised to power x equals minus 0.6180. Now, e is a positive number. A positive number raised to power anything can never be 0. If you don't get that, just try taking log on both sides and you'll see your calculator will give you an error for ln 0. That's not possible. So you don't get anything from this equation. This is not possible. Okay, you can try solving this and you'll get an error. Similarly, the last one, this is also not possible. A positive number raised to power anything cannot give you a negative result. So this is also not possible. Again, if you were to try taking log on both sides, on the right side, you would have log of a negative number, which is not possible. So that doesn't give you anything as well. What about the second case? This is going to give you ln e raised to power x. On the other side, you've got ln of 1.618. Take x on the side here, and that becomes x ln e equals ln of 1.618. Ln e is just 1. You just evaluate ln of 1.618 and see what that turns out to be. This gives us 0.481, and that is your final answer. If you were to use just 1.6 here, your answer would be something different. It could be 480, 482, 483, and that could make you lose 1 mark for inaccuracy at the end. Okay, so keep that in mind. 4 significant figures for working at a minimum. Any questions on this? Any problems with this? No? Okay, let's move on. Let's move on to another example now. So this was 33. Let's see if we need to do more. This is doable. Okay, yeah, this is a good one. Have a look at that. This is very similar. 13. Yeah, let's do these two. So sometimes you could have modulus along with logs as well. Since we have already covered the modulus function, we could try doing this. This is question number 21 from the worksheet. We need to solve this equation first of all in the first part, 4x minus 1 modulus that equals modulus of x minus 3. Now, remember what we used to do for such equations? We just used to put plus minus on any one of the two sides. We could say 4x minus 1 equals plus minus into x minus 3. Now, split this into two parts. You have 4x minus 1 equals x minus 3, or 4x minus 3 equals minus into x minus 3. The first equation gives you 3x equals minus 2 and x equals minus 2 over 3. The second equation gives you 4x minus 3 equals minus x plus 3, and that's 5x equal to 6, x equals 6 over 5. These are the two answers that I'm getting from this first part. Okay, minus 2 over 3.
Sir,
And is there something wrong here?
4x minus 1.
Oh yeah, sorry about that. So this was 4x minus 1, not 3. On the left side, this is 4x minus 1. That's 5x equals 4 and x equals 4 over 5 and not 6 over 5. Sorry about that. So these are the two possible answers that we've got. But remember, whenever we solved modulus equations, what did we say? We said we always should verify our answers by inputting in the original equation. So you should verify these answers. In this case, they will be correct because you've got modulus on both sides here. In that case, you don't have a problem generally. So these will be the two solutions that you get from this equation. But you should still verify just in case. Let's look at the second part. The second part says, hence solve this equation. All right, correct to 3 significant figures. Now, what did we do in the first part? So hence suggests that we should be using the first part somehow, right? Now, in the first part, we solved this equation. 4x minus 1 modulus, that was equal to modulus of x minus 3. And this was giving us two answers. One was x equals minus 2 over 3, and the other was x equals 4 over 5. In the second part now, they're asking us to solve this equation. 4 raised to power y plus 1 minus 1 equals 4 raised to power y minus 3. This is the second part. We need to find the values of y from this equation. And they're saying you have to use the first part somehow. Now, what does that mean? If you were to compare these two equations, what is the difference? You see, you got minus 3 here, you got minus 3 here. You have minus 1 here, you have minus 1 here. But the other two terms are different. This is x, and in place of that x, what you have here is 4 raised to power y. So that basically tells you, in the first equation, what has happened is you've replaced x with 4 raised to power y. That is what has happened. Now, how does that work here? Well, you could actually write 4 raised to power y plus 1 as 4 raised to power y into 4 raised to power 1. If you just rearrange this, that's 4 multiplied by 4 raised to power y. And again, if you compare with what is there in the first equation, you just replaced x with 4 raised to power y. So that is what is happening. In order to go from the first equation to the second equation, x is being replaced with 4 raised to power y. So that's exactly what you do here as well. You don't have to solve all of this again. You know from the first equation, x was equal to minus 2 over 3 or 4 over 5. Second equation, you could say, just replace x with 4 raised to power y. So either 4 raised to power y equals minus 2 over 3 or 4 raised to power y equals 4 over 5. All right, these are the two possibilities that you have here. Now, what about this? This does not give you anything because it's 4 raised to power y equal to a negative number. Now, you can't get a negative number as an answer here. If you try taking log, you would realize that the right-hand side would turn out to be undefined. You can't take log of a negative number, but you can simplify this second equation. This is 4 raised to power y equals 0.8. If you take log on both sides, you get ln 4 raised to power y equals ln of 0.8. Y comes down here and it becomes y ln 4. That equals ln of 0.8. And y equals ln 0.8 divided by ln of 4. And that's going to give you the value of y that you were looking for. Okay, you can solve this and see what that gives you. The values of y, the value of y that we get here is minus 0.161. That is the answer that we get from this. Okay, there's only one answer. And that's it. Make sense? Any issues with this? Any questions?
No, sir.
No? Okay, one last question, then we start linear law after that. Okay, one last question. Which one was I thinking about? Yeah, so this one, question number 13. Let's do this one last question. In this, you're using a different log with base 2. Let's just try this. And then we end. This was question number 13 from the worksheet. All right, so show that this equation can be written as a quadratic equation in x. Now, how does that work? You have log of x plus 5 with base 2, that equals 5 minus log of x with base 2. So how do we deal with equations like these? Remember, one possibility is that you take all the log terms to one side. Okay, let's start with that. Take all log terms to one side, log of x plus 5 with base 2. Plus log of x with base 2. On the other side, you've got 5. And now on the left side, you need to try and make this a single log, convert this to a single log term. How will that work? You've got addition outside log. So if you were to make it one single log term, it becomes multiplication inside log. That's x plus 5 multiplied by x, and the base of this log is 2. So you've converted it to a single log. Addition outside, it becomes multiplication inside. On the other side, you've got 5. And now you can take this base 2 to the other side and make it the base of 5. And that gives you x plus 5 into x on the left side. On the right side, you have 2 raised to power 5. That's x squared plus 5x minus 32 equals 0. This is a quadratic equation that we've got. This is what we were supposed to do in the first part. And now in the second part, it says, hence solve this equation. Now that's straightforward after this. It's a quadratic equation. We can solve this quadratic equation. You can see if factorization is possible. 32, you could use 8 and 5, x squared plus 8x minus, no, 8 and 5, 8 and 3, they're not gonna work, I'm sorry. Nothing works here, I think. Does anything work? 8, 3, 9, 4, no. So you can't factorize this, you have to use the quadratic formula. Minus 5 plus minus square root of 5 squared minus 4 into 1 into minus 32. Just input values in the quadratic formula, and then you can write down the answers. Okay, see what you get from this. The values of x from this quadratic formula. Okay, so one is 3.68 and another is x equals minus 8.68. These are the two values that we get from this. Now remember, whenever we are solving equations that have log in the question itself, in this case, we've got log term in the question, we've got multiple log terms in the question, you have to think about the answers. Are they going to be acceptable to those log functions? Are they going to make any term undefined? If you were to input minus 8.68 in this log will become undefined, and this log will also become undefined. So that's not possible, right? So minus 8.68, you'd have to ignore this value. 3.68 is a positive value, and it's not going to cause any problems here in any of these two logs. So that is fine. But the second answer will need to be ignored. You would say this is not possible. And that's enough. You don't have to write any reason for this, but you have to make sure that you cut it out. You say that this is not possible. So the only possible answer that you have is 3.68. This is your final answer. All right. Now, if there are no questions on this, let me quickly give you a hint about this one. I just had a look at this. So when you're doing this, you can't use substitution. You got 5 as the base here, 3 as the base here. Substitution is not going to work, and you also have don't have any plus signs within the terms, between the terms. So you can just start by taking log on both sides for this particular question. So I'm talking about question number 14. If you were to take log on both sides like this, ln of 5 raised to power 2x minus 1, and on the other side you have ln of this whole thing, 2 into 3 raised to power x. Now you can't bring this x outside yet. You would first have to apply multiplication law on the right side. So on the left side, you would have 2 minus 1 whole multiplied by ln 5. So that power is going to come down. On the right side, you would first have to split it into 2 parts. You would say this is ln 2 plus ln of 3 raised to power x. And then you could bring this power down because now it's the power of this whole thing. Earlier, we had 2 inside. X was only on 3, not on 2. So you could not use the power law there yet. Now you could write it like this. This is x ln 3. And then you could just solve it further after this. Simplify this, simplify the left-hand side, and make x the subject. And that would give you the result. Okay, so be careful on the right side here. You have to first use the multiplication law and then the power law, and then it's going to work like that.